we'll get started. So I'm really excited to present Tyrone Ghaswala, who will be talking about subsurfaces and covers in the wild world of infinite type surfaces.
Right. Thanks so much for having me. It's really nice to speak in person. This is my first conference since the world shut down. And I've seen a lot, I've met a lot of you in online, and it's nice to, finally see your feet. This is everything I talked to you about today is joint work with these two people. So the first half is with both of them, and then the second half about covers is just with Alan. Frederic is in Paris, Alan's in Glasgow. That's him in his natural habitat. Well, he's in Madrid, but he's almost always in Glasgow, in the Scottish wilderness. All right. So because everything's work in progress, please, I don't mind how far I get. Just interrupt. Make me stop. It's fine. No problem. Okay, great. Maybe not. Maybe not so great. Oh, sorry. Just I have to agree that I'm being recorded. Okay, we're good. So here's what you're in for. This is your last chance to leave and go see Maggie's talk instead. So we're going to abstract and construct homomorphic subsurfaces and finite sheet covers of infinite type surfaces. I will explain all those words by the end of the talk. And here's the plan. We're first going to talk about the classification of surfaces, infinite and finite type. We'll then talk about homomorphic subsurfaces, then we'll talk about the covers story. And the cover story is a work in progress, which I'm pretty excited to talk about. It's lots of fun. The goal of the talk today is to convince you, if you're not already convinced, that infinite type surfaces are worth thinking about, and failing that, to convince you that infinite type surfaces are enjoyable to think about. Because at some point in grad school, everyone has this moment where you're just like, man, this is awful. And you got to remember, you got to remind yourself that mathematics is actually a lot of fun. There's a lot of crap that goes on around it, but like, the math is fun. This is what we're here for. So this is what I'm going to try and convey today. All right. Sigma is going to represent a surface all day, every day. My surfaces are orientable, so they're real two manifolds. Second countable, none of this long line BS. All right, they're orientable and they're boundaryless, unless I say otherwise. Okay. Cool. A surface is finite type if its fundamental group is finitely generated. For example, this fella here. Infinite type if not. If there is no finite generated set for its fundamental. All right, let's roll. So here, my favorite theorem of all the mathematics is the classification of finite type surfaces. This is the theorem that got me into mathematics. I saw it first in a high school math camp where all the cool kids go, and it was just like, there's no way to do anything else but to see this. So it's excruciatingly powerful. It's so powerful that we use it every day without really thinking about it. So what does it say? Is that a surface is determined by two numbers, which is the genus and the number of ends. Now I'll talk about what an end is in a moment, but for right now, it's just like a way to go out to infinity or something. So here I've got a genus 1 surface with two boundary components deleted. Right, so this is a boundaryless manifold. There's no boundary. And it has sort of two parts you can go to where there's no, you're sort of going out to infinity. There's no boundary to stop you from falling off, and you can keep walking out there. Even though it doesn't look like it by this picture. Here's a genus 0 surface with 3 punches. So blue X's throughout the talk are just going to be deleted points from my manifold. So this has genus 0 and 3 ends, whatever an end is. And here's an example of a genus 3 surface with 0 ends. Right? It is really powerful. So I want you to consider the following thing. I can have a conversation with someone and be like, oh, I'm thinking of a 3-sheeted cover of a genus 2 surface. So a genus 4 surface. Right? Like, this is amazing that you can say this. It's something that we take for granted all the time. It's like extremely powerful. The classification of finitely generated abelian groups. Like, these classification theorems are incredibly powerful. We use them without really thinking. Even better, you give me any two numbers, there's a surface with genus G and number of end ends. Right? It's just like, it's a beautiful, it's as nice as you could ever want. So what about infinite type surfaces? That was the finite type classification. What about infinite type surfaces? Well, here's an example of one. This is a Loch Ness monster. For reasons I hate, but it's fine. We're calling it the Loch Ness monster. So it's just like you got infinite genus going off in one direction. Here's what's called the ladder, a better name. So infinite genus going in two directions. By the way, if you're second countable, you can only have countably many geni. Here's another example. I can take the plane and then delete every integer coordinate. That's going. It's not just a square, right? It goes up in every direction. Here's another example. This is a flute. Good name. Looks like flute. You can play uncountably many notes. Just keep going off in that direction. There's like these kind of tubes that just go off to infinity. That's what I've drawn here. Yeah, so this has some depth to it, like you have a curve going around. That's a flute. You can take S2, and because you're a masochist, you can remove a Cantor set from it. Right, that's an artist's impression of a Cantor set. You could take an infinite trivalent tree and then inflate it, and then look at the boundary of that. Or you could do that and then put genus at every vertex, if you felt like it. Things just get worse. That's called a blooming Cantor tree. Or you can take this thing. So this is, I've taken 2 copies of R, and then at every integer coordinate, I've connected them by a tube. Sorry, 2 copies of R2. That's what I should say. Or you can take this surface. It's like genus going off there, there, and there, and then there's some punctures going off in one direction. There's another surface. Madness. It's just no control. Off the rails, these things. So here's all the pictures I just drew, and which are homeomorphic? That's the question we should be asking right now for the first part of the talk. Which of these are homeomorphic? Right. I like it. All right. Okay. Good. Let's talk about the ends. I wasn't always like this. I had children a while ago. I can't help it now. Okay, so let's think about how we're going to identify the ends. How we're going to talk about what an end is. So intuitively, you want an end to be a way out to infinity. Right, so on this picture, you should expect an end going that way and an end going this way, and ends at these punctures. Right, there's sort of a deleted point. But there's a couple of ways you might see this in the literature. One of them is like this. There's an inverse limit of complementary components of compact subsets, which is great if you want to minimize the number of lines you want to write your definition of. Okay, but we're going to take a different approach, which is a little more intuitive and really captures what it means to go out towards an end. Right? So the idea is that you want to talk about one-ended rays. So these are just copies of the half of an integral. And each of these is sort of an example of that, except you want them to be proper. Okay, so an end is an equivalence class. I'll tell you what the equivalence class is, of a continuous map into your surface from 0 to infinity, close at 0. Right, so that's where the sort of ball is on each of these rays. What does proper mean here? So proper is your pre-image of a compact set is compact. This is not a proper image. It's a continuous image, but it's not proper. Right? You can think of like a compact disk surrounding the whole thing, and the pre-image of that is not compact, it's a whole thing. So that's garbage. We don't want things like that, and properness exactly captures what we actually want. All right, now what about the equivalence relation? Because somehow, like, I can have another arc going out to the right, I could have another ray going out to the right there, and you wanted to define the same yellow end. Okay, so we want these two to define the same yellow, the same end. You might say, well, I want them to be homotopic or isotopic. Right? But that's too weak, because it turns out that any 2 images of this in your surface are homotopic. You can like shrink it via a tan function or something, and then turn it and shrink it out. Anything's homotopic, that's useless.
I mean, you're not fixing any.
I'm not fixing any, I'm not fixing the endpoints or anything like that. That's right. And then you might say, okay, maybe I want proper homotopy, so I can't like shrink and then expand. But that's too strong because these two arcs are not properly homotopic. So you need something in between. And it turns out that the right notion to have is this. Right? So it's like a homotopy, except it's a homotopy only when you restrict it to integer points on your arcs on the way out. Okay. So here it's a homotopy for the naturals cross 0, 1. And basically the picture you have is, so what I've drawn is the image of that homotopy. It's just like you've got a ladder. And as long as you can connect the two arcs all the way out, you're good to go. But I've got this proper thing here, which is really important because you might say, Ty, I can join one of the yellow arcs to one of the blue arcs by a ladder as well, because I can take the first point joined by a second point joined by an arc, third point joined by an arc, right? And that would also give me a homotopy of this form, right? And it would look something like this. But this is not going to be proper because consider this compact set, this green curve, it's compact. The preimage of that is going to be an infinite discrete subset in your ladder, which is not compact. So this is also garbage, right? You can't have this kind of thing happen. So properness, when you deal with non-compact spaces and topology, if you're not talking about proper things, you're missing something. Properness is really the important adjective to have in front of most things when you talk about non-compactness. Right? Preimage of compact sets somehow is the right definition for a lot of stuff. So that's what an end is. So an end is an equivalence class, and we call this an equivalent class of one-ended arrays, and we call this a set of ends. Any questions? Need to drink.
Can you repeat why it's not proper?
So the previous,
Yes.
this guy?
Yeah.
Yeah, so I want the preimage in here of a compact set to be compact. Now imagine I've done these red lines like infinitely often. And I'm looking at the preimage of that green compact set. So what does this look like? It's like countably many integrals. And the preimage of the green arc is going to be a point on each rung.
Yeah.
And that set is not compact. Yeah. Good. So we're going to topologize a set of ends. It's not good enough to just have a set of ends. We want to put a topology on it. Here's how it goes intuitively, and then I'll write down the definition. You take your favorite compact set. You look at a complementary component. So there's my complementary component. And then you look at all the rays, all the one-ended rays, which have, so all the sets of ends. Start again. You look at all the ends which have a representative, which is a one-ended ray contained in that complementary component. Right, so here are two one-ended rays contained in that complementary. Those form your basic opens. So it's a topology generated by these sets. All the ends which have a representative contained in a complementary component of a compact set. Okay. Great. We're almost there. There are two flavors that ends come in. There's these ones, which are ends accumulated by genus, which means as you walk out to infinity, as you follow one of these one-ended rays, you keep seeing genus. You might say, what's the definition of genus? It's just like you keep seeing curves which are non-separated. Curves, when you cut along them, you still end up connected to surface. So there's two ends accumulated by genus here, and all the other ends are what are called planar ends. Well, they're not accumulated by genus. All these blue ones. So all these punctures are planar, and then there's a big end out here. Any questions? Yeah.
Is there a sense in which the end accumulated by more punctures is like
It's different.
different, like more of
Yes.
an end? You can't see it.
I'll get to that in a second. Yeah, you'll see why it's different as well. There is a notion, but not like separating. Yeah. Okay.
Hi.
Yes. Oh, sorry.
Hi.
Conscience. Okay. Yeah.
It's
Go ahead.
me, God. No. What if you drew this? What if you drew a picture where you had like an infinite strip with no genus along it? Is that basically just a puncture, or?
An infinite strip with no genus. Yeah, that's Yeah, that's just an isolated non-planar end. Sorry, planar end. It's just a puncture. Like you
Okay.
could replace that with a puncture and it would be a homeomorphic surface.
Okay, thanks.
Okay, so what is this topological? So remember we had a set and a topology on it. Let's draw the topological space. All these are isolated, all the punctures, because I could think of a compact set that just surrounds it, like a little curve, and then it's the only end inside that conformation component. So these are all isolated. That's what I've drawn here, right? Those blue dots are all isolated. Out here, they accumulate to this big end, and this is what Brian was asking. Right. So here you've got this big end, which all these isolated ends accumulate to. And then up there, you've got all these isolated planar ends accumulating to a non-planar end, to an end accumulated by genus. And then over on the right, you've just got an isolated end accumulated by genus. Cool. Questions about this picture? This is a picture of the space of ends of this surface. That's the topological space. It's nice, it's compact, it's got all kinds of cool properties. In fact, let's see what properties it has. Here are some nice facts. The end space of any surface is homeomorphic to a closed subset of the Cantor set. Now, the Cantor set is maybe a little misleading, but the Cantor set has a nice universal property that if it satisfies some adjectives like these three, if it's these three and every point is not isolated, then you're homeomorphic to the usual Cantor set, like your middle thirds Cantor set as a topological space. And if you remove that last one, you're homeomorphic to a closed subset of the Cantor set. So it turns out in the space of like compact, totally disconnected metrizable spaces, this is all of the things that can happen. So you prove that the end space has these properties, and then you appeal to some point set topology theorem that tells you you're homeomorphic to a closed subset of the Cantor set. Even better, the ends accumulated by genus, which is a subset of your whole end space, is closed. So you have a closed subset of the Cantor set and a closed subset inside that. Always you have that done. So these are facts. You should prove them if you're bored.
Why can't I get like bare space? I take like a sphere minus the irrationals or something like this.
What's going to happen is you'll have a point, so at infinity, I guess, which is not like it doesn't have a neighborhood homeomorphic to like R2.
Okay. Oh, and then it stops being a manifold.
Stops being
Okay.
Exactly. That's a good question. Okay, so now we can talk about the classification. You have some data given to you. I have a surface atom data. The data is a genus, which can be infinite, and this topological pair, which is the end space and the ends accumulated by genus living inside. And up to homeomorphism, you're determined by that data, but it's the homeomorphism type of that pair. All right, so if you have two surfaces with homeomorphic pairs of topological spaces as their end space, then they're homeomorphic as surfaces. So you can think of this like you're starting out at infinity and then you're rebuilding the surface inside. It's good enough. Great, this is amazing. It's like kind of magic that you can have a classification of all. What does this tell us from the examples before? It turns out that this space here has one end. Exercise. So it's homeomorphic to this. But it's not homeomorphic to this because this has two ends. These two spaces are homeomorphic. Exercise. This only has one end, one big end and a whole bunch of isolated functions. Anyway, their end spaces are homeomorphic.
Should you see that as wrapping this power with force make the point, I guess? And trying to visualize
Maybe-
why that space is as a single end and not four.
Yeah, I mean this is like going off to infinity.
Yeah, so you kind of wrap it up.
Yeah. I have a hard time thinking about what the homeomorphism actually looks like. But yeah, I know that the theorem tells me that it's homeomorphic. These two spaces are homeomorphic because they have homeomorphic end spaces. Sure enough, because there's some justice in the world. You know, when you remove a Cantor set from a sphere, the end space is a Cantor set. Which is good. And you have a Cantor set of ends here. And the way you see that is, you know, every time you get to choose whether you're going left or right for your one-ended ray. So you get an infinite sequence of zeros and ones. That's in bijection with the counter set. It's that. Even better, you give me any possible data, it's attained by some surface. So you give me a genus and a topological pair of closed subsets and a Cantor set. There's a surface which gets you there. It's as good as it gets. And remarkable that there's a classification theorem at all. All right. Why? Who cares? This is a question you should always be asking yourself constantly. So there's a few reasons. Like there's a danger of just abstracting for its own sake, right? Especially like, oh, let's just look at all surfaces because we can. So first, if you walk up to a surface in the street, you should expect it to be infinite type. This should be the generic case. Asking for a surface to be finite type is very special. It's nice because we have theorems that let us deal with them, but it's very special. So if you take like a foliation of a three manifold or something, the leaves are going to be infinite type. It's just like, it's not going to be the case generically that you have finite type leaves. These things pop up in nature all the time, and we don't really think about it. We don't think about the topology of them very much, but we should, and we are now. So mapping class groups are really interesting to think about. We've seen some talks about them already. There are examples of big mapping class groups, which are mapping class groups of infinite type surfaces, are examples of non-compactly generated, non-locally compact groups, which typically you can't get your hands on. But this provides a full rich family of groups which you can actually play with that are not locally compact. And we have so many tools to sort of probe them because we have all geometric group theory that we're trying to import. It's a really fantastic area. And remarkably, there's a classification. Again, whenever you have a classification, just exploit it. You have to. You have no choice. You're compelled to exploit it. It's part of your contract as a mathematician. All right, so that's the classification. Sorry, are there any questions about the classification?
Yeah, I have a question.
Yeah, go for it.
There's like a 40-year gap in the yeah, what's the like history?
Yes. Oh, okay. Someone in the audience can correct me. But what I understand is Carachiato had a proof of this part, and maybe there was like a little bit of an error or a gap, or no, it was all good.
No, it was not.
Oh, it was not all good. Thank you, Rosa. And then Richards came along, and in his thesis, I think, proved this very like generously. It's like, oh, I'm just doing what he kind of thing, but like he corrected it, and then constructed the surfaces. Did the full story. Yeah, that's the story. I'm not sure why the 40-year gap, and then you could probably ask why the 40-year gap from Richards to what we're doing now as well. Like, yeah, and I don't have a good answer for that.
Do we see the difference between the non-planar ends and planar ends in the topological?
In the topological?
In the topological space of the ends.
No, you have to actually like determine them. You have to like point them out, color them a different color as I do. Yeah. You can't see it just in the top. Okay. Great. Let's talk about some subsurfaces. So here is an example of a homeomorphic subsurface of this surface, register green part. It's homeomorphic to the genus 2 surface with one boundary component, but it's kind of cheating. And what do I mean by cheating is that the inclusion map is homotopic to a homeomorphism. Here is an example of what we're calling for this talk a strict homeomorphic subset. In the finite type world, you can prove using like Euler characteristic arguments or fundamental group or something, some invariant to show that finite type surfaces don't admit strict homeomorphic subsets. This surface does. And I want to tell you about one theorem, which we proved a while ago, is that every infinite type surface admits a strict homeomorphic subset. And here's a picture of the proof. So this is kind of interesting. It's like, you know, infinite type surfaces behave like fractals. I don't know what you want to think. What the moral lesson is here, but it's true. So here's an example of a strict homeomorphic subsurface of the flute. Right, this is a flute. what I'm gonna do is I put all the features in a plane at every integer coordinate, and then I just look at like the upper half plane, something like that. And that turns out to be a homomorphic subsurface. And this effectively, this is not the proof that's in the paper, but this is sort of how we stumbled upon it. This is effectively the picture you do. Any surface, using the classification, you try and convince yourself that you can draw it as something where you put some feature at every integer coordinate, and then something else somewhere in the upper half plane, and then just take the upper half plane. And that's your homomorphic subsurface.
Is there a similar characterization of the Cantor stuff? Like you take any subset that's infinite?
So, I mean, if you take any clopen subset of the Cantor set, it's homomorphic to the Cantor set.
Is that useful? This?
I think it's like morally kind of the same thing what's going on, but we don't actually use that fact. No, that's not entirely true, right? I know that what's sort of up there is a Cantor set because of the property of the Cantor set. Yes. And then I can use the classification of surfaces to tell me that that's actually homeomorphic to what I started. Great. All right, let's talk about covers. That was subsurfaces. Well, we use that to construct a hyperbolic graph that the mapping task group acts on. That's a story for a different talk. I want to just talk about the topology of infinite type surfaces. So let's talk about finite sheeted covers of finite type surfaces, and then we'll talk about infinite type ones. Here's the genus 2 surface with 3 boundary components. I know I said there's no boundary, but I lied a little bit. Let's just have some boundary here. The Euler characteristic of this thing is -5. You can check. I don't think I made a mistake. Let's say we had a 3-sheeted cover. Euler characteristic is multiplicative of the covers, so I know a couple of things here. I know that the Euler characteristic of sigma tilde better be -15. But I know more things because I know that each boundary component, if I restrict my attention to it and I look at its pre-image, is a cover of the circle. Okay? It's a 3-sheeted cover of the circle, but it might not be connected. So what does that mean? So I can conclude that my Euler characteristic is -15 and the number of boundary components upstairs. For each boundary component downstairs, I have between 1 and 3 upstairs. So I have to have between 3 and 9 boundary components upstairs. Here's a theorem of Massey from the 1970. Is that arrow I drew up there is an if and only if. So if you have a finite, so you have a k-sheeted cover of a surface over another surface with boundary, let's say oriental, etc. If and only if the Euler characteristic is multiplicative and the number of boundary components satisfies this inequality. That's it. It's a very nice paper. It's like 4 pages long. This constructs, the gist of it is, given boundary components that satisfy this, you construct a cover. That's where the word is. So everything that can happen does happen. That's the moral of the story. This is a really beautiful little fundamental paper. Matt Sinet says it's been cited twice in all of history. I think it's kind of remarkable. I'm not exactly sure what's going on there. We're going to be the third, it'll be great. Okay. So when you talk about finite sheeted covers, you should talk about commensurability. So what does it mean for 2 surfaces or topological spaces or whatever to be commensurable is if they share a finite sheeted cover, a common finite sheeted cover. You might have seen commensurability in a group theory sense, and group theory, it says that the groups have isomorphic finite index subgroups. This is kind of the translation. Exercise this is an equivalence relation. It's not obvious, but it is an equivalence relation. The sheets of these don't have to be the same, by the way. This could be like a 2-sheeted, this could be 3-sheeted, that's fine. That's what it means to be commensurable. So 2 surfaces are commensurable if they share a common finite sheeted cover. And here's a nice theorem, which is a consequence of Massey, which is that commensurability classes, their equivalence classes, fall into one of 6 cases. You either have boundary or you don't, and your Euler characteristic is either -0 or not. Right, so here's an element in the commensurability class, or that commensurability class, empty boundary with negative Euler characteristic. These are all the hyperbolic manifolds, the hyperbolic closed ones. These are all the Euclidean ones. These are all the spherical ones. Same thing, but with boundary. commensurability, this notion of showing a finite sheeted cover is actually telling you about the geometry, right? Somehow it's the next finest classification. Homomorphisms like common one-sheeted cover. But this is common finite sheeted cover. So it naturally, looking at commensurability classes naturally gives you a way of sort of grouping your surfaces. And you would hope that commensurable surfaces share some properties. And it clearly does here, because there's some geometry going on. It's kind of, it's really fascinating. In three manifolds, there's a beautiful story, which I'm not going to talk about, but like there's really interesting questions in hyperbolic knot theory of what are the commensurability classes. It's like open problems, and it's really fascinating. And it's not something you hear people talk about a lot. I think it's a really cool area. Okay.
Hi.
Yes. Ethan.
Are we requiring that these covers be connected?
Yes.
Okay.
Please. Okay. Great. So what are the, I mean, I've been sort of hinting as to what the questions are going to be. Right? What are the finite sheeted covers? If you walk into two infinite type surfaces on the street now and you ask, does one cover the other? That's one question you want to ask. And the other one is, what are the commensurability classes? Let's go back to that. What are the commensurability classes of infinite type surfaces? Why would we care about this question? Well, you know, maybe this is a way of organizing our thoughts. Is that first we look at this commensurability class proves something about this because they're all kind of similar. Something about this. Now, there's going to be uncountably many commensurability classes. We can prove this and it'll come up later. So it's not entirely a way to get at all of them, but it's a way to organize ourselves. Right? We need some way of doing bookkeeping. Even though there's a classification, it's unwieldy. We need a better way. So commensurability classes is something very fundamental about infinite type surfaces that we don't understand. And you think finite sheeted covers, no problem, we should be able to do that. That's what Alan and I thought. No, it's not as easy as we were hoping. It wasn't supposed to be a project, but you know, we got hooked on the question. Let's look at some examples of finite sheeted covers of infinite type surfaces. I just want to say something else. So there's lots of, there's lots of sort of beautiful mathematics that's come out of mapping class, big mapping class groups, or the geometry of mapping class groups. The geometry in both the geometric group theory sense and the hyperbolic geometry sense. There's lots of like automatic continuity, beautiful questions like that, which are great, but we don't understand the surfaces as well as I would like. We should do both. We should be able to understand the surfaces and we should understand these other questions. So I think this is important. It's like a very fundamental question. All right, let's look at this first cover. So I've set up this three-ended infinite genus surface in such a way that it has 2 pi on 3 rotational symmetry. But even better, that action is free, right? Because the only fixed points you would expect actually end up right in that genus. So it's a free action. So if you take the quotient, it's a covering map. Great. Maybe you can convince yourself that this covers a ladder. Right, because what's going on is each of these 3 ends is being identified on the quotient. Somehow, something's going on. Here's another example. I'm going to take a tube, and then on the top and bottom, glue on genus, all the way in both directions, except at one point where I glue on like a ladder going up and going down. And now this has 2-fold rotational symmetry. Because the axis is running through the middle of the tube, it's a free action. So there's a cover. These 2 ends end up mapping to the same end, and those ends, they just sort of map as a one-to-one map. That's those 2 ends on the left. So this is kind of strange. I've got a regular cover, regular 2-sheeted cover of a 3-ended surface by a 4-ended surface. Or I have an irregular 6-sheeted cover by doing that and then that of a 4-ended surface, of a 1-ended surface by a 4-ended surface. Covers are great. I really like them. They're good. You can see that maybe things are going to be a little more interesting than we thought. Okay. So finite sheeted covers are good for the following reason. When you have a finite sheeted cover, the covering map is a proper map. So the pre-image of compact set is compact because you only got finite sheets. What that tells you is, so this is like a general fact about non-compact topological spaces. If you have a proper map between them, it induces a continuous map on a set of ends. This is an exercise you can do. Here are some disappointing observations. Sorry. There's going to be some disappointing observations. Let's say one more thing about this first. When you have infinite type surfaces, you don't have many tools at your disposal because it turns out they're all homotopy equivalent. Every infinite type surface has fundamental group, infinitely generated free group, and the universal cover is contractible. So they're all k-pi1s, so they're all homotopy equivalent. Ooh, you can't use any of that at your disposal. So really you've got like proper homotopy is your one tool you have, and looking at the space events. These are your sort of main tools you can use to probe the surface. Right, so that's what we're going to look at. We're going to look at this map on the set of space events. Okay, here are some disappointing observations. Sometimes you write down statements and you're like, math is beautiful, it has to be true. And then it's false. So the first observation, both of these are actually given by the following covering space. Okay, so let's take a bit of time and talk about what we've got here. So I've got like a thickened up ladder first, all right? So I've got like tubes here, sort of fat, and I've drawn this curve here to indicate the depth. And what I'm going to do is I'm going to take out punctures from the middle of the genus so that I have an axis that I can rotate around and it'd be free, right? I want to do like a hyperelliptic evolution where I like skewer this thing and then give it a 180-degree flip. But if those punctures weren't there, this wouldn't be a free action. So I'm just going to puncture it. And now it's going to be a free action. And just for fun, I'm also going to puncture the top and bottom. And I'll just draw those peaks so we can keep track of which ones are going away. Okay, the end space of this surface is like a bunch of isolated planar ends accumulating. Oh, I didn't draw it. Sorry, this should be two ends, but anyway. It's accumulating to an end accumulated by genus on the right and the same story on the left. That's an incorrect picture there. It should be the same story on the left. If I look at the quotient, all the genus vanishes. So first thing, this doesn't respect the ends accumulated by genus. Covering maps don't respect the ends accumulated by genus. Genus can vanish. And the second thing is that let's look, so you would want P bar to be a covering map because it would make a nice theorem. But it's not. That's not the way math works, unfortunately. And the way to see this is that out really close to the end, right to the left, let's say, the map is 1-to-1 at the end, but on any neighborhood, there are these pink ones which are 2-to-1. So there's no neighborhood of the big end where it could possibly be a homomorphism. So you kind of have a local homomorphism. Yeah.
Why do we expect it's reasonable to have to not respect this, the ends accumulated by genus?
Because your classification theorem somehow has something to do with ends accumulated by genus. So maybe we're hoping that it's true, but it's just not. I mean, it's not reasonable because it's not true. So, I mean, maybe I went in being too naive.
Also, the flower petal cover you get, I mean, I guess that one, it's like a third of the infinities.
Yeah, but you still have, like somehow in that one, you still have genus, right? You still have an end accumulated by genus. So what you would want, maybe you don't want this, but what I wanted is that if your end over here was accumulated by genus, then it's going to be accumulated by genus over here. But this shows you it's just not true. This red one becomes white.
Carrot, what is those like opposite direction, like the base space?
Yes, so what's true is that if downstairs you're accumulated by genus, then your pre-images are all accumulated by genus. That's true. You can't create genus by going upstairs. Yeah, you can try to think about why that might be true. Okay, so it doesn't respect your ends. It's not a covering map. Boo. All right. But here's an encouraging proposition which really makes everything go. And this comes out of studying this map by thinking of ends as one-ended rays. Here's why, because one-ended rays are contractible. And contractible things always lift to covers. Somehow this is like, it's too convenient. It's very suspicious. Okay, so this is sort of the main tool we use. We just stare at that really hard and then try to prove little properties about the map. So if you have a K-sheeted cover, it turns out that the map on the space of ends is continuous, it's open, it's surjective, and the preimage of any point has the most K points. So they're the things you would expect, but it requires a little bit of proof. Things you would hope would be true anyway, I think. Okay, so it kind of feels like a covering map, right? The open surjective part, at least. You know, that's kind of like a covering map. It's kind of like a branch covering map. Okay, cool. So you get an immediate corollary, which I think is kind of neat. Is that if you have a finite sheeted cover and your surface upstairs is a monster, then your surface downstairs has to be a monster. No choice. Cool. Nice little corollary. Having finitely many ends is a commensurability invariant. So if you have two surfaces, one has infinitely many ends and one has finitely many ends, they're not commensurable. Same with, I could replace finitely with countably, and it would still be a commensurability invariant. All right, good. We got a little bit of progress. Let's prove some more things. It turns out that the covering map doesn't respect whether or not your end is accumulated by genus, but it does if the end is isolated. This is kind of interesting. If you have isolated ends accumulated by genus, you can't get rid of the genus from it. I don't know what's going on. I mean, we could prove it, but like something interesting is happening. So this map P bar respects whether or not you're isolated in planar, and it respects whether you're isolated in non-planar or accumulated by genus. So you have another corollary like we did last time, is that a punctured, so you take a ladder, a monster and puncture it. That's what I've drawn there. If that's upstairs, then that has to be downstairs too. You have no choice.
And along the same lines, can I say that you're going to respect like the Cantor-Dixon rate feminine?
That does. It's a slide I deleted because it was too long. But yeah, that's absolutely what happens. The Cantor-Dixon rank of an end is preserved, which turns out to be very powerful to have that lemma in your back pocket. It also tells you the following: that if upstairs you have a flute, this requires a bit of work from here. It's not an immediate corollary, but if upstairs you have a flute, then downstairs you have a flute. And remember I said before that you can tell whether or not your end is a Cantor set by asking whether or not you have isolated ends. So if you have no isolated ends, your end space is a Cantor set. You might have some genus thrown in, but no, the whole end space is a Cantor set. That's a commensurability variable. This is kind of neat. If I have a surface where the space of ends is not a Cantor set, a surface where the space of ends is a Cantor set, they're not commensurable. They share no common finite sheeted cover. Again, maybe it's not surprising, maybe it is surprising. I don't really know. Oh, that's weird. All right. Deja vu. Okay. So now that we have those, we can talk about some commensurability classes. So we've produced some commensurability invariants, like having finitely many ends or something like this. But now we want to construct covers to try and work out what the full commensurability classes are. So here's a theorem, is that if you have finitely many ends, there are two commensurability classes. And they are the commensurability classes of the once punctured monster and the monster. So if you have some planar ends, you're going to be commensurable to this. If you have no planar ends, you're going to be commensurable to this. Remember, this is all an infinite type. So there's two commensurability classes for finitely many ends. So this comes from some set theory and something about this Cantor-Dixon rank that Brian mentioned before. But I'm just going to state it without proving it, and we can talk about it after if you want. But if your end space is countable and every end is accumulated by genus, we can prove that if you give me an ordinal, it's came out of nowhere, but if you give me an ordinal, there's exactly one commensurability class for every ordinal, for every countable ordinal. And this tells you there's uncountably many commensurability classes because there's uncountably many countable ordinals. So, you know, I go through grad school like avoiding this stuff like the plague. And it just comes back. I really like it. I think it's really beautiful that you have all this like ordinal set theory stuff coming up, and it turns out that countable closed subsets in a Cantor set, you can look at them as ordinals. There's like a theorem from 20s which tells you this, the 1920s. Yeah.
Are there continuum many or just?
There's omega 1.
And I mean, like, are there continuum many commensurability classes?
Yeah. Yeah. Are there continuum many?
Like,
Are there continuum many countable ordinals?
no. I mean, there's only omega 1 countable.
Oh yeah.
So,
I
like,
don't
the-
distinguish those in my mind, but yeah.
is-
Sorry.
Okay.
You're right. You're right. All right, and then the theorem I want to talk about a little bit about how we actually construct the covers is, so before I said that having a Cantor set of ends is a commensurability invariant. Anyway, so not only is it necessary for two surfaces to be commensurable, but it's sufficient. Right, so if you give me any two surfaces which have a Cantor set of ends, they share a finite sheeted cover. And I'm going to show you how, and this was the most surprising thing we came across, how a blooming Cantor tree covers a Cantor tree. So for a long time when we started this, we were just trying to prove that the blooming Cantor tree lives in its own commensurability class, and it doesn't cover anything else, and nothing else covers it, because it felt like that should be true. And then a couple of weeks in, I got a text from Alan. He's like, I did it! They're not commensurable. It's just like, there's no way this is true. Anyway, sure enough, turns out that the blooming Cantor tree can cover the Cantor tree. So let's see how this works. I'm going to build this cover for you. And this is a good model for how you build all covers effectively. You build them up from finite sheeted things. Here's the building block we're going to use. This is a two-sheeted cover of a genus 1 surface with 4 boundary components over a genus 0 surface with 4 boundary components. And you're skewering this genus 1 surface through those boundaries, which are no longer there, and then rotating by pi. And the quotient is a sphere with 4 boundary components. The covering map restricted to these boundary components is a degree 2 map of S1 over itself. That's your building block. So we're going to keep that in our back pocket, and we're just going to like exploit it over and over again. So let's start with that. So I've drawn it a little bit differently. Because I've drawn my covering of a genus 1 with 4 boundary components over a genus 0 with 4 boundary components. And I've told you which boundaries are being mapped to which boundaries by coloring them. And now what I'm going to do is I'm going to take this picture again and take each piece. These are genus 1 with 4 boundary components covering genus 0 with 4 boundary components. And the colors are telling me how everything's going to get glued together. And because every single boundary is mapping to the corresponding boundary by a 2-to-1 map, I can glue these things together and the cover's going to extend. It looks like that. And now you rinse and you repeat.
That's great.
Oh, and then you rinse and repeat. No, I'm kidding. I didn't draw it okay. I thought about it and I was like, no, I'm going to go and have dinner with someone. Okay. Good. So this is how you construct a cover. Pretty neat. Okay. I'll finish that.
Are there any questions for Ty?
Is there any book to say anything interesting about the infinite sheeted covers?
Right. There are interesting things you can say, but I think it's too unwieldy. So I'll give you a couple of examples. So first is like a one-dimensional example. So R has 2 ends, and it covers S1, which has 0 ends. So immediately you're in trouble because you can't talk about the ends. But you can have a 2-sheeted cover. Sorry, you can have an infinite sheeted cover of a two-ended surface by a one-ended surface, which is kind of weird because you're like creating an edge. And here's how you do it. So all right, we're gonna play a little game. You take your R2, and at every integer coordinate, you glue on a handle, every integer coordinate in all directions. And now I'm going to shift by 1 in the x direction, let's say. And quotient out by that. That's a free action by Z. What happens is, like, there's a sort of a cylinder of a fundamental domain, the ends get glued together. So now I have a two-ended, and what that is it's a monster covering a ladder, an infinite sheet cover.
Sorry,
Okay.
that please.
Yeah, sure. So you happy with this picture of the monster with the genus at every integer coordinate? And now I'm going to shift by 1 in the x direction, let's say. So that's a Z action and it's free, so I can quotient out by it. And the quotient you can think of as taking like the lines x equals a half and x equals minus a half and gluing those together. Because that's what gets identified. So now it wraps around and now I've got this cylinder with genus on top. That's what the quotient is. That's a two-ended surface. So I started with a one-ended surface and now I've got a two-ended surface, which hurts. So, I mean, there's hope of saying something. I'm not exactly sure what. Whether you'd end up proving a theorem like everything can happen. So it's not interesting or not. Yeah, I don't know. But commensurability somehow, right? Like, it's telling us. Commensurability is telling us which groups of surfaces to place together. We're not choosing. Right? We're not saying, oh, I want to put all of these together because they kind of look the same the way I draw them. We're letting the finite sheeted coverness tell us which ones should be similar. That's the idea. And somehow, you know, finite sheeted we could get a handle on. Infinite sheeted, there's more that can go on. Yeah, there is a hope. We just haven't. I mean, this is work in progress. You can tell there's no clean sort of overarching theorems yet. Maybe there never will be. But yeah, maybe there's something to be said. If you had control over what kind of infinite sheeted covers, maybe you could say something. Yeah, it's a good question. Yeah, right.
So in like the group theory land, you talk about commensurable groups. You can also talk about like more general equivalence relation, like, you know, quasi-isometric groups and stuff like that. Is there a profitable business of talking about like quasi-isometric groups? Does this translate to groups of infinite type surfaces somehow nicely?
So I mean, commensurability. So in the two manifolds and three manifolds, three manifolds anyway. Commensurability of manifolds corresponds to commensurability of groups because the manifold is determined, its homeomorphism type is determined by the fundamental. In infinite type world, all the groups are the same. They're all commensurable anyway. They're all infinitely generated free.
Okay.
So somehow you don't, there's no obvious translation. There might be, but
There's not one you know of.
there's not one. Yeah, from the usual translation to groups that you get in the finite type world, there's no similar thing going on. That's right. Yeah.
All right, so what do you think is going to happen if you start adding in that?
If they start adding in boundary components. My guess is that the covering map is probably going to respect all your boundary end data, like whether it's an infinite and how those accumulate. Just a guess. The reason I'm saying this is because finite sheeted covers, you know, your circles are going to have to map to circles, and your lines are going to have to map to lines. Somehow that should be good enough to tell you that all that data is preserved. Again, yeah, we just picked the safest, easiest family to start with randomly.
Oh, yeah.